Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and in today's class we will learn about the concepts of paging related to memory management. The learning objectives for today's class are learning about the concept of paging to understand what is meant by pages and frames, and to understand how the logical address is mapped onto the exact physical address when paging is the memory management scheme that is being used. So, we learned in the earlier module that any process that needs to be executed should be present in the main memory, and we also learned that process can be put as a whole contiguously into main memory. And while putting this process contiguously into main memory, the main memory can be divided into static partitions, and the process can be put into the partitions fully as a whole, or you can have dynamic partitions. Based on the size of the process, you can put the process into whichever place is free, or whichever hole is free in the main memory. And while putting a process into the main memory, there are different ways in which you can try to put the process into the main memory. You can have first fit, where you find the first hole which is big enough to accommodate the process and put the process into that particular place, or it can be a best fit, where you look at the smallest hole which is large enough to accommodate this process and put the process into that particular hole, or it can be worst fit, where you find the biggest hole and that should be big enough to put the process into it, and that is called worst fit. And you can have any of these allocation strategies based on which you can put the process into the main memory. The problem with this kind of memory management or memory allocation is that it will result in external fragmentation. That is, it is possible to have holes here and there in the main memory which are large enough to accommodate the incoming process, but it is not present in one particular place, or it is not present as one big hole, so that the process can be brought in. The process is brought in here and is put as a whole. The process is not broken into pieces. The process has to be put as a whole into the main memory. So, having holes here and there will not be helpful to put the process inside, and hence need to go for compaction, where you try to bring together or put together all the holes that are present here and there into one big hole, and then try to bring the process in. So, this is what we had learnt in the earlier module, in the earlier class about memory management. And in today's class, we learn what paging is. And the memory management scheme that we describe here in today's class does not want the physical address space of a process to be contiguous. So, it will help the physical address space of the process to be non-contiguous. That is, your process is not put as a whole into the physical memory, into the main memory. It can be broken into pieces and can be put into the physical memory. So, the process can be allocated the physical memory wherever it is available. It need not be one big hole where you need to accommodate the entire full process. So, what is done in paging is that the physical memory is divided into fixed sized blocks called frames or page frames, and generally this size is always a power of 2, which can be between 512 bytes and 8 kilobytes. And the process is also divided into pieces of same size, which are called pages. So, the logical memory that is corresponding to the process is also divided into blocks of the same size called pages. And we also need to keep track of all the free frames in the physical memory. So, we have the physical memory being divided into pieces called frames, equal sized pieces called frames, and the process being divided into equal sized pieces called pages, and these pages can be put into the physical memory or need to be put into the physical memory, and hence we need to know which are the frames that are free in the physical memory. So, if you need to put a program of size n pages, you need to find n number of free frames and then put all these pages into the free frames that are available in the physical memory. And these n free frames need not be contiguous, they can be in different places. So, now when you have put the pages of the process into the physical memory in different places, you need to remember where each page of a process has been put in the physical memory. For that, a data structure or a table is maintained which is called the page table. So, this page table helps to translate the logical address that are generated to the exact physical addresses where the pages have been put in the physical memory. But the problem here with paging is that it may result in internal fragmentation. Now, look at this example. You have a process whose logical memory is divided into 4 pages: page 0, page 1, page 2 and page 3. And the physical memory is also divided into different frames. Now, here in this figure we see that there are 8 number of frames in the physical memory, and these pages in this process are being put into the physical memory. So, page 0 is put into frame number 1 and page 1 is put into frame number 4, page 2 is put to frame number 3 and page 3 is put to page number 7. As I told you, we need to remember where exactly or in which frame in the physical memory the pages have been put. Only then we can do the translation from the logical memory to the physical memory. So, we need to have a page table. Here a page table is shown in which we remember where in the physical memory the page has been put. So, page 0 has been put in physical frame number 1, that is entered in the page table. Similarly, page 1 is put in frame number 4, that is also entered in the page table. Very similarly for page 2, which is in frame number 3, and page 3 which is in frame number 7. So, from the page table we can understand where in the physical memory the page has been put. And as I told you, we need to maintain a list of free frames, so that whenever a page has to be put into the physical memory, whenever a process is brought in and it has to be placed in the physical memory, the operating system can look into this list of free frames and understand which frames are free, and then the pages can be added to those free frames. Now, here a new process arises which has got pages 0, 1, 2 and 3. There are 4 pages for this process, and you have a free frame list which says that frame number 13, 14, 15, 18 and 20 are free. The frames 16, 17 and 19 and 21, they are already occupied with pages of some other process. And so, what is done? This process has got 4 pages, and the 4 pages are being added into some frames in the physical memory. So, page 0 is added to frame number 14, page 1 is added to frame number 13, and page 2 is added to frame number 18 and page 3 to frame number 20, and all these are entered in the page table for this particular process. And you need to understand here that each process has got its own page table. So, the mapping of the pages of a particular process will be in the page table of that particular process. Very similarly, you will have page tables for every process in the system. So, this frame table is something which maintains details about the free frames that are present in the system. It should give details about which frames are currently allocated, which frames are available, how many total frames are there in the system, and so on. So, for each physical page frame, you have an entry in the frame table, and each entry will give details on whether the frame is free or it is allocated, and if it is allocated, it will give details about which page of which process is currently using that frame. Now, we will see an example of how different frames are allocated for different processes when multiple processes come in and go out. As you all know that a process, while it is under execution, it has to be present in the main memory, and you need to allocate space for that process in the main memory. Say it is not being used currently, the process pages that are allocated to that process can be removed from the main memory, and some other process can be given space in the main memory. Now, look at this example where you have process A. Process A has got 3 pages, page 0, 1 and 2, and these are the frames that are present in the main memory. And now, when this has been placed into the main memory, or initially say all frames were free, and hence when this page table of this process is placed into the main memory, you see that process A's page 0, page 1 of process A, page 2 of process A, all these are kept in the main memory, and you also may update the page table of process A. So, in frame 0, page 0 is kept, in frame 1, page 1 is kept, frame 2, page 2 is kept. So, the details are updated in the page table. Now, another process needs to be brought into the main memory. There are 4 pages for this process, and we have enough frames in the physical memory, and hence all the 4 pages can be placed into the physical memory. And once all the 4 pages are placed into the physical memory, see here you place the pages of page 0, 1, 2 and 3 of process B into the physical memory, and you also update the page table of process B. So, you remember that page 0 of process B is kept in frame number 3, and page 1 in 4, page 2 in frame number 5 and page 3 in frame number 6. So, that is also updated. Say another process arrives, say process C. Process C has got only 2 pages, and the 2 pages of this process is kept in 2 frames in the physical memory, in frame number 7 and frame number 8. Now, say process A leaves, or maybe it is terminated and process A leaves, and hence what happens, the memory that was allocated to process A in the physical memory are now been freed, and the page table of process A is removed, the process A itself is now not existent. Now, we have 3 frames that are free here, and then one last frame that is free here, and some of the frames are occupied by process B as well as by process C. Say a new process, process D comes into picture. This process D has got 4 number of pages, and you need to put all these 4 pages into the physical memory, but contiguously you do not find 4 free frames in the main memory, but the first 3 are free and the last one was free. So, what is done is the first 3 pages are occupied by the first 3 pages of process D, and the last frame here is occupied by the last page of process D, and you update the process table of process D accordingly. So, you have 0, 1, 2, 1, 2 as the frame numbers for the first 3 pages, and 9 as the page number for the last page. Likewise, you can bring in processes and take out processes from the physical memory, and you can make use of the page table to remember which process page is kept in which physical frame. And hence, here you see that each process will have its own page table. Now, you have pages that have been placed onto the frames. You have a page table which remembers which page was kept in which frame. Now, whenever an address is generated by a particular process, you need to know how to translate this address into the exact location where it is kept in the main memory. So, processes are kept in the main memory, addresses that are generated by the CPU for this particular process need to be mapped on to the exact location where the content is present in the physical memory. For this conversion, what is done is the logical address that is generated by the CPU is divided into two parts. One is called the page number and the other is called the page offset. So, this page number is actually used as an index into the page table to find out the frame number, and from the frame number you get the base address of the frame where this particular page is kept, and then to that you add the offset to get the exact physical location. So, look at this diagram. This just shows how a logical address is converted into a physical address. So, you have the CPU which is generating logical addresses. The logical address, as I told you, is divided into two parts, a page number and an offset. So, this page number is used as an index into the page table. So, the value of P is used as an index here. So, I get an entry in the frame table. This frame table entry will be nothing but the base address of the frame in which that particular page is stored, and that is added to the offset which you get from the logical address to get the exact physical address. Look at this example now. Here you have the logical memory of the process. There are 4 pages in this process, and each page is of 4 byte size, and you have a page table. Because there are 4 pages, you will have 4 entries in the page table. So, the page table, the number of entries in the page table is equal to the number of pages that are present in the logical address space, and these 4 pages are put into the physical memory. The physical memory is also divided into the same sized frame. So, the size of a frame in the physical memory is also 4 bytes, and first page logical addresses starting from 0, 1 to 3 is placed in frame say from 20, 21, 22, 23, and EFGH, that is logical address from 4 to 7 is placed in this frame, that is it is placed from 24 to 28, and you also remember where you are placing the pages. So, the first page is placed in frame number 1, 2, 3, 4, 5, 6. So, frame number 6, since you are indexing from 0, it just noted as frame number 5, and then next is placed in frame number 6 and so on. Now, we will see how a mapping is being done from the logical address to the physical address. As I told you, the size of each page here is 4 bytes, and this 4 is nothing but 2 power 2. So, whatever be the size of the page, you need to express it in terms of a power of 2. To address 4 locations, we need 2 bits. So, just with 2 bits, you can address one of these 4 locations. So, to address one of the locations within a single page, you need 2 bits, because you have 4 different locations within a particular page, and this 2 bits will go as the offset in the logical address. Suppose if the logical address is a 4-bit address, the 2 bits will go for the offset and the remaining 2 bits will go as a page number. So, now consider this logical address 1, say the logical address that is generated is 1, that corresponds to this B. So, 1 can be written as 0, 0, 0, 1. So, 0, 1 will be the offset and 0, 0 will be the page number. Now, what happens during an address translation? The page number is used as an index into the page table. So, 0, 0 is used as an index into the page table, which corresponds to the first location. And the first location, you see that the frame number is 5, and each frame has got 4 bytes. So, 5 into 4 is 20. So, this corresponds to 20, that is starting of this page corresponds to the starting of frame address 20, and to this 20 you add the offset, that is 1. So, 21. So, 21st location in the physical memory has B, which corresponds to this logical address 1. Now, consider another logical address, say 10. 10 is the 10th location here, that is corresponding to K, and 10, if it is written in binary, it will be written as 1010. 10 decimal written in binary as 1010. And again here this 1010 is divided into 2 bits for the page number and 2 bits for the offset. So, 10 is used as the page number and it is used as an index into this table. So, what is 10? That is 2. Binary 10 corresponds to decimal 2. So, that corresponds to this location 2 and the corresponding frame number is 1. And the frame number 1 into 4 will give you 4 plus this 10 again is 2, that is binary 10 corresponds to decimal 2. So, 4 plus this 2, the page number, the frame number plus the offset will give you the location corresponding to this, that is K. So, this is how the logical address is converted into the physical address. Similarly, whatever be the size of the page, here we have considered an example where we have only a page size equal to 4 bytes, but the page size can go even up to 8K bytes. So, whatever be the case, based on the size of the page, the number of bits have to be allocated for the offset and the remaining will go for the page number, and based on that you do the address translation from the logical address to the physical address. Now, we see an example here. Say consider you have a logical address space of 8 pages and each page is of 1024 words, that is 1 kilobyte, and each is mapped onto a physical memory of 32 frames. So, what is the data, and we need to find out how many bits will be there in the logical address and how many bits will be there in the physical address. See how the mapping is done from logical address to physical address, that is the logical address space should be divided into a page number and an offset, and use a page number as an index into the page table, get the frame number, add it with the offset to get the physical address, actual physical address. Now, we need to now find out here in this problem how many bits will be present in the logical address. So, the logical address, as I told you, is divided into a page number and an offset. So, we need to first find out how many bits will be present in the offset or how many bits will go into the offset. How do you find out how many bits will go into the offset? For that you need to use, you need to find out the page size. So, what is the page size that is given here? He says the logical address space has got 8 pages, 8 pages meaning the number of pages is 8 and each page is of size 1024 words. So, the size of the page here is 1024. 1024 can be expressed in powers of 2 as 2 power 10. So, since 1024 is equal to 2 power 10, 10 is the number of bits that should be used for the offset. And how many number of pages you have got? You have got 8 number of pages. So, to address one of these 8 pages, you need to have 3 bits because 8 is 2 power 3. So, to address one of the 8 pages, you need to have 3 bits. So, 3 bits will go for the page number. So, 3 bits for the page number and 10 bits for the offset. So, the logical address should have 13 bits. And what about the physical address? And the physical address also you have the same frame size. So, 10 bits will be for to address one of the locations within a particular physical frame, and remaining how many bits to address one of the different frames that you have got. How many number of frames you have got here? You have got 32 frames. So, 32 can be expressed as 2 power 5 and hence you have 5 bits needed for addressing one of the 2 power 5 frames, and hence you have 15 bits for the physical address. 10 bits to address one of the different bytes you have in the physical memory or within a particular frame, and then the remaining 5 bits to address one of the different frames that you have available in the physical memory. And now this paging does not have external fragmentation. Why no external fragmentation? Because you have got fixed size frames in the physical memory, and you are putting only these pages into the fixed size frames. So, you will not have holes here and there which can be combined together into one big place and so on. That does not happen here, but you have internal fragmentation. How is internal fragmentation possible? Say if the size of the process is not a multiple of the page size, say if the page size is 1 kilobyte and if the size of the process is 10 kilobyte, it will exactly sit in 10 different pages. But if the size of the process is say 10 kilobytes plus some 100 bytes, the extra 100 bytes will go and sit in the 11th frame. The 11th frame will not be fully used. So, just look at this example. If the page size is 2048 bytes, you have 2 kilobytes as the page size, and the size of the process is 72,766 bytes, and to accommodate this process of size 72,766 bytes, you will need 36 frames. That is 35 full frames, and the remaining 1086 bytes will sit in the 36th frame. So, here you find that the frame size is 2048, but in the last frame only 1086 bytes will be occupied. So, the remaining bytes 2048 minus 1086, that is 962 bytes, will not be occupied at all. So, the space which is not occupied will get wasted, and that is called internal fragmentation. So, in the worst case, what can happen is that if you have a page of size n bytes, only 1 byte will be occupied and the remaining n minus 1 bytes may get wasted. So, on the average, it is found that 1/2 page gets wasted for a particular process. So, how do we avoid this? We can say that we can go for smaller page sizes. So, if smaller page sizes are used, then the disadvantage will be that we need to have an entry in the page table corresponding to each and every page in the process. Now, when the page size becomes smaller, the number of pages will get increased, and because of that the number of entries in the page table will also get increased. And when you are transferring pages from the disk to the main memory and then again back from the main memory to the disk, you will be transferring small page sizes. Rather than that, disk I/O will be more efficient when the number of data being transferred is much larger. But now these days larger page sizes are used, and there is even a possibility that have been proposed by researchers that on the fly page size can be provided. So, the page size will not be fixed, that can be variable, that can be fixed on the fly depending on the size of the process that is arriving, so that you avoid internal fragmentation or reduce internal fragmentation. So, summary for today's class is that we learnt about paging, in which we understood that a process is divided into equal sized pieces called pages, and the physical memory is also divided into the same sized pieces called frames, and these pages can be put into any frame in the physical memory. And there is a free frame list which is maintained by the operating system, which keeps track of which frame is free in the physical memory, and whenever pages are being put into the frames, then the free frame list is updated as to which process that particular frame is allocated and so on. And then you have a page table. This page table remembers which logical page of the process is put onto which frame in the physical memory, and this helps in address translation. Using the page table, the logical address is divided into two, a page number and an offset. The page number is used as an index into the page table to get the frame number. If the frame number is added to the offset to get the actual physical address. And in the case of paging, it is possible to have internal fragmentation because pages and frames are of fixed size. If the page size is not a multiple, if the frame size is not a multiple of the page size, then you cannot accommodate the process exactly onto the pages. There can be one page, one last page that is allocated to the process which is not being used at all. So, the references, acknowledgement. Thank you.